Welcome to the Professional Machine Learning Engineer Crash Exam course. Today we will focus on a Retrieval-Augmented Generation, or RAG. RAG is the architecturally correct solution for factual grounding at inference time. It supplies exact facts, while fine-tuning ensures the correct format. The process starts with unstructured data that is loaded, split, and embedded into a vector store. Chunking typologies, such as overlapping, semantic, and hierarchical, impact retrieval quality. Pre-retrieval transformations like query rewriting, high DE, and multi-query improve search. A post-retrieval re-ranker is the final quality gate, reducing hallucination by filtering irrelevant chunks. Filtered chunks and the original query go to context assembly, feeding the LLM to generate a grounded answer with source citations. RAG outputs are uniquely falsifiable, allowing human verification. The latent space is a mathematical construct where similar concepts are clustered. Distance metrics, such as L2, dot product, and cosine similarity, measure relevance within this space. The search spectrum includes dense semantic search, which matches meaning, and sparse keyword search, which focuses on exact term matches. Reciprocal rank fusion combines both for maximized recall and precision. KNN is computationally expensive and unscalable. Approximate nearest neighbors, like HNSW, sacrifice slight accuracy for massive speed, using techniques like IVF and PQ to optimize search and reduce memory footprint. GraphRag uses ontology for structured constraints and hybrid embeddings for rich text descriptions. This surpasses flat vector stores by enabling multi-hop reasoning and ensuring traceability via schema logic. LangGraph topologies shift AI from linear data fetching to iterative autonomous reasoning loops. Key components include the agent, state, nodes, and conditional edges that govern the routing decisions. The AI agent core utilizes 4 types of memory: working memory for context, episodic memory for past paths, semantic memory for facts, and procedural memory for operational workflows and skills. The interceptor layer, or semantic cache shield, provides instant answers. It uses entity masking and adaptive thresholds, with cross-encoder verification and eviction policies to prevent memory issues. Faithfulness measures how much a generated answer is supported by retrieved context. Secondary evaluation metrics include context precision, context recall, and semantic similarity. The production diagnostic board links failure stages to symptoms, root causes, and architectural fixes, ensuring robust RAG system maintenance and performance improvement. Beyond flat text, RAG architectures extend to multi-modal RAG, using CLIP embeddings for cross-modality retrieval, and tabular RAG, which injects live, structured SQL executions into the generation prompt. RAG is the architecturally correct solution for factual grounding at inference time. It supplies exact facts, while fine-tuning ensures the correct format. Compared to fine-tuning in long context windows, RAG is highly efficient and low risk for hallucinations. The RAG process begins with unstructured data, which is loaded, split into chunks, and vectorized using an embedding model before being stored in a vector store. Contextual retrieval, by augmenting chunks with metadata, improves search precision. Pre-retrieval transformations like query rewriting, high DE, and multi-query help clarify ambiguity and rephrase queries. Post-retrieval re-ranking is the final quality gate, reducing hallucination by discarding irrelevant chunks before the LLM sees them. Filtered chunks and the original query go into context assembly, which is a prompt template for the LLM. The LLM generates a grounded answer with source citations. RAG outputs are uniquely auditable and falsifiable. Latent space is a mathematical construct where semantically similar concepts are clustered together, and distance equals relevance. L2, or Euclidean distance, is the shortest straight-line distance, while cosine similarity is the angle between vectors, which is the default metric for semantic search. The search spectrum includes dense semantic search, which matches underlying meaning, and sparse keyword or BM25 search, which relies on exact term matches. Reciprocal rank fusion, or RRF, marries these methods to maximize both recall and precision. KNN is computationally expensive brute force. ANN, or approximate nearest neighbors, sacrifices slight accuracy for massive speed. HNSW, or hierarchical navigable small world, uses multiple layers for coarse navigation and local precision to find nearest neighbors efficiently. GraphRag uses ontology for structured logical constraints and hybrid embeddings for rich text descriptions. This surpasses flat vector stores by enabling multi-hop reasoning and guaranteeing traceability via strict schema logic. The Neon Hacker blueprint details LangGraph topologies, which moves AI from linear data fetching to iterative autonomous reasoning loops. Key components include the agent LLM, state, nodes, and conditional edges. An AI agent core uses different memory types: working memory for short-term context, episodic memory for case-based reasoning, semantic memory for factual knowledge, and procedural memory for operational workflows, updated via reflection. The interceptor layer, or semantic cache shield, provides an instant answer and reduces load on the LLM node. It uses entity masking, cross-encoder verification, adaptive thresholds, and eviction policies to maintain efficiency and accuracy. Faithfulness measures how far the model has hallucinated beyond its sources. Secondary evaluation metrics include context precision, context recall, and semantic similarity, focusing on the quality and relevance of the retrieved context and generated answer. The production diagnostic board links failure stages, symptoms, and root causes to architect fixes. For example, retrieval issues are addressed with hybrid search and query rewriting, while generation issues require strict guardrails and faithfulness evaluation. RAG extends beyond flat text to multi-modal RAG using clip embeddings for cross-modality retrieval, and tabular RAG, which injects live, structured SQL executions into the generation prompt. The core blueprint remains the same: binding external reality to generative reasoning.